Welcome back to Digital Systems 1, and today we're going to be learning about a new device called flip-flops. So by the end of the video, you should be able to interpret the output of a flip-flop given both synchronous and asynchronous input conditions, and we'll discuss what all of that means throughout the video. So far, the logic circuits that we have discussed have been combinational circuits. And those are the type of circuit where the output only depends on the input at that moment in time. In other words, so far we've only dealt with circuits and systems that have no memory of the past and only operate based on the present moment. The flip-flop, or the latch, is a memory element made up of logic gates that are connected in ways that permit information to be stored. So when you start to think about all of the ways that we save data between the cloud, your computer, your phone, flash drives, CDs, DVDs, if we go back in time and think about the concept of digital memory, it all begins with the idea of a flip-flop or a latch, which is a memory element and can store a 0 or a 1 until it's needed later. The way that the flip-flop and the latch work is they use what's called feedback. That means that certain gate outputs are fed back to certain inputs. And there are several kinds of flip-flops, and we're going to discuss the most common types in this particular video. When we look at the flip-flop, there's a diagram or a symbol that we'll use to represent a flip-flop. It's usually labeled like this. FF means flip-flop. You'll have a certain set of inputs, and depending on the flip-flop, those inputs will change. But the basic idea behind any flip-flop is that you have an output, which we call Q, and then you have an inverted output, which we call not Q. And depending on what the inputs are, and depending on what kind of flip-flop it is, your Q will be based off of those inputs. And definitely, when we think about a flip-flop, we think about also the output states. If Q is 1, we call that the high state. We also call that the set state. When Q is 0, we call that the low state or the reset or clear state. So when we say the flip-flop has been cleared, that means that the output Q is low. If we say the flip-flop has been set, then the output Q is 1. So these are the output states that we'll refer to when we discuss how a flip-flop works. The flip-flop has other names, including a latch and bistable multivibrator. That's another word for a flip-flop. The first type of latch we're going to discuss is a NAND gate latch, or simply just a latch. It's a very basic flip-flop. It has two inputs, set and clear. Sometimes clear is also called reset. You can see in the diagram on the left how the flip-flop is wired. And that concept of feedback is evident when we see that the input of one NAND gate is the output of another. That's feedback. And the truth table for this NAND latch is in the middle here. And the truth table is based on the two inputs called set and reset. So when set and reset are both 1, the output won't change. What that means is that whatever the output was before, it continues to be the same way. If the output was previously a 1, it's still a 1. If the output was previously a 0, it's still a 0. We call that no change. If set goes low while reset goes high, the output becomes a 1. The output is set. If the input for set is 1 while reset is low, then the output is low. We call that the clear or reset stage. And then if both inputs are low, we call that an invalid state. Invalid state. Logically, based off of how these NAND gates work, if both inputs are low, it produces an output where Q equals not Q. That can't happen. Q and not Q can never be the same. We call that an invalid state. So you would never intentionally set the inputs of this latch to both be 0 because you don't know what the output will be. It'll be unpredictable and it will be incorrect. This is a symbol that we also use to represent the latch. Notice that the S and the R have a bar on top and a bubble in front. When you see an input that's labeled with both a bar and a bubble, that's called an active low input. That means if I want to activate this input, I have to send a low signal. And we can see that in the truth table right here. In order to set the flip-flop, I had to send a low signal to the set input. In order to reset the flip-flop, I had to send a low signal to the reset input. These are called active low inputs because of the fact that it takes a low to do whatever that input it was designed to do. Active low inputs. You'll always see the bar and the bubble will let you know that those are active low inputs. So on your notes, you'll have a waveform for the NAND latch. And I want you to use the truth table and the inputs provided to figure out the output for the NAND latch. When you're doing problems involving flip-flops, there's memory involved. So you can't really decide what the output is unless you know what the output was before. So you're always going to be given an initial condition for your flip-flops. So I want you to assume that Q is initially 0, hit pause, and try to determine the Q waveform, the output for the NAND latch. All right, and here's the waveform you should have. Notice that when set and reset are both 1, there's no change. Q is initially 0, which means it's going to stay 0. When reset goes low, that active low input, when reset goes low, it triggers the flip-flop to have an output of 0. The output was already 0, it's just going to continue to stay low. Then when set and reset both go back high, no change. When set goes low, now this active low input is going to trigger the flip-flop to set, or to have an output of 1, based on the truth table right here. So when set is low while reset is 1, Q is going to be high. So at this point, the flip-flop is going to toggle or change states and go from low to high. When set goes back to 1, while reset is still 1, no change. It was 1 before, it'll stay 1 again. And set goes back low right here, which means the flip-flop will be set. It was already 1, it's just going to stay 1. And then we can see right here, reset goes low while set is high. This is when the flip-flop will clear and the output will go low. That's how we would do the waveform for a NAND latch. So I'm now going to show you an application of a NAND latch. It's almost impossible to obtain a clean voltage transition from a mechanical switch because of a phenomenon called contact bounce. And when we're talking about switches, I want you to think about the data switches on your breadboard. Those switches have to go from 0 volts to 5 volts depending on how you maneuver them. But sometimes it's impossible to get a clean transition from 0 to 5 or from 5 to 0 because of something called contact bounce. The action of moving the switch from low to high or high to low produces several output voltage transitions as the switch bounces. So when you are changing your switch, you might be thinking you're going from high to low or low to high, but there's actually a little bit of oscillation in there. And oscillation is never good in a digital system. You can only ever have a high or a low in a digital system. You don't want an input to switch very rapidly between the two, which is what can happen with contact bounce. The multiple transitions on the output signal generally last no longer than a few milliseconds. But a few milliseconds is a long time in the digital world where things happen extremely fast. So we don't want contact bounce, especially when we're working with flip-flops. You don't want to have that phenomenon happen. A NAND latch can be used to prevent the presence of contact bounce from affecting the output. And here's an example. Let's say that this is your switch. And as you maneuver the switch from high to low or low to high, this is the bounce that we're talking about. See how this signal was very noisy? It goes up and down very rapidly, very quickly, and it's not very smooth. This is not the type of signal that you want to be sending into something like a flip-flop because the flip-flop won't really know how to interpret it. When you insert a flip-flop into the equation right here, as your switch moves from high to low or from low to high, you get a nice clean transition. So the output of that switch will be connected to some other piece of your circuit, which will then get a smooth transition from 0 to 1, as opposed to getting this bouncy signal. This is a very undesirable input. This is far more desirable, and the application of a NAND latch allows that signal to be nice and smooth. That's just one of many applications that you'll see for a NAND latch. You can also create a latch out of NOR gates. It operates exactly like a NAND latch, except that the set and reset inputs are now active high rather than active low as they were before. You also notice this in the picture. There's no bar and no bubble on the S and the R inputs. If there's no bar and no bubble, that's an active high input. That means if I want to set the flip-flop, which means I want to force the output to be 1, I have to send a high into this input. If I want to reset the flip-flop, that means I want to force the output to be 0. I have to send a high to the reset input. And that's exactly what this truth table shows me. If both the inputs are low, no change. If I want to set the flip-flop, I have to send a high signal into the set input. If I want to reset the flip-flop, I have to send a high signal into the reset input, and that will clear the flip-flop. And with this flip-flop, when they're both high is our invalid state. We don't want to intentionally set both inputs of a NOR gate latch to both be 1. You get an invalid output. Notice this is what it's going to be wired like internally with the feedback loops, the same way as the NAND latch. So the important thing to remember here is that the set and reset inputs are active high. The output will change whenever one of these inputs is high. Take a look at your notes and you'll have a waveform for the NOR latch. And you have 2 inputs, set and reset. Q is initially 0, and try to determine the output waveform for Q based off of the truth table for the NOR latch. And here's what you'll get when you solve that. You'll see that the flip-flop is set here because set goes high. That's an active high input. So if I want to set the flip-flop, I have to set this high while reset is low. And you'll see that it's set right here. Anytime that both of the inputs are low, no change. So for example, set goes low here, reset is low here, no change here. It was high before, it'll continue to be high. Right here's where the reset is now activated, and now the flip-flop is going to be cleared. And it's going to toggle from high to low because the reset input was activated with a high signal. Again, if you follow the truth table, you can see that when set is low while reset is high, the output has to go low. And that's what happens here. We can see that in this period of time, there's no change because both inputs are low. Right here, the flip-flop is cleared again because this input goes high. It was already cleared before. It's going to continue to stay cleared. And then lastly, you have set and reset, where set goes high and reset is low. Here's where the flip-flop will be set once again, and the output will change from 0 to 1. This is how we would do the waveform for a NOR latch. Next, we're going to talk about flip-flops that have something called a clock. And a clock is based off of the idea of a digital pulse. It's a rapid transient change in the amplitude of a signal from a baseline value, which is normally 0 volts, to a higher value, which is normally 5 volts, followed by a rapid return back to your baseline value. A positive pulse can go from low to high. This is an example of what a positive pulse might look like. A negative pulse will go from high to low. This is an example of what a negative pulse might look like. You have what's called transition times a rise time, which is labeled as T_R, and you have the rise time here. And then you have what's called the fall time, which is T_F right here and right here. And that's basically the amount of time it takes to go from low to high or high to low. So you have your transition times, your rise time, your fall time, and then you have what's called the pulse width, which is labeled here. And the pulse width is the time between the points when the leading and trailing edges are at 50% of the high voltage. This is for a positive pulse. So you can see here, the pulse width is defined as the time it takes to go from when the leading and trailing edges are at 50% of the high voltage. So the pulse width is approximately the time it takes to go from here to here. These are some of the values that we might use when analyzing a pulse or creating a pulse. A clock signal is a rectangular pulse train, or some people call it a square wave. So it's a successive line or a succession of pulses that just continue to happen one after another. This is what a clock signal will look like. It's going to be an even square wave where the amount of time that it's low is exactly the same amount of time that it's high. The clock signal is what's going to be distributed to all parts of a system. And when we're talking about systems, we're talking about systems that use flip-flops. Most, if not all, of the outputs will change only when the clock makes a transition. And when we say transition, we're talking about a transition from high to low or a transition from low to high. So, like I just said, transitions can be defined as going from 0 to 1. That's called a positive going transition. So when the clock signal goes from 0 to 1, that's called a positive transition. We also call that the rising edge of the clock. A transition can also be from 1 to 0, which is a negative transition. And in this picture, the negative transitions all have arrows pointing down. That's called the falling edge of the clock. Transitions are also called edges, so you'll hear that term used interchangeably. Again, remember that when the clock signal goes from a 0 to a 1, we call that a positive going transition, or a PGT. When it goes from a 1 to a 0, we call that a negative going transition, or an NGT. So, a clocked flip-flop has a clock input that works like I just described as one of its inputs. And the flip-flop will make a transition at its output only when the clock makes a transition at this input. So the clock kind of starts to control when the output will change. Another way to think about it is that the flip-flop is only activated by a transition in the clock signal itself. So set and reset might be up here, and set and reset can change how they want to, but Q won't change until the clock makes a transition. And we have two different types of flip-flops. Those that are activated by a positive transition and those that are activated by a negative transition. If the clock is activated by a positive transition, the circuit diagram will look like this. This is your clock input right here. If it's activated by a negative transition, you'll have a bubble right in front of the clock input. That lets you know that that flip-flop will not respond. It will not change its output. Q will not do anything until the clock makes a negative transition. So the small triangle is what will tell you where the clock signal goes. Again, no bubble means it is activated by a positive transition. And if you see a bubble, it indicates that the clock input is activated with a negative transition. Clocked flip-flops have one or more control inputs. Those are things like set and reset. These inputs have no effect on the output until the clock makes its transition. Positive to negative or negative to positive. So the control inputs have no effect. Since they are synchronized with the clock, We call these synchronous control inputs. Synchronous control inputs. That means that they have no effect until the clock makes a transition. The control inputs get the flip-flop ready to change the output, but the transition in the clock signal is what actually causes the change to happen. So here's our first example of a clocked flip-flop. This is called an SR flip-flop, S for set, R for reset. Notice the clock signal would be right here. There's no bubble, so we know that the flip-flop would be triggered on a positive transition. And let's look at the truth table for this flip-flop. So when S and R are both 0, no change to Q. Doesn't do anything. When S is 1 while R is low, that's the set state. So the output is going to be 1. But the output is not going to physically change until the clock makes its positive transition. That's what this column means. If set is low while reset is high, the output will be 0, but not until the clock makes a transition. And then this state right here, when they're both 1, we still call that an ambiguous or an undefined state. You wouldn't intentionally try to have your flip-flop have 2 inputs of 1. Now we're going to do a waveform for the SR flip-flop. And we're going to keep in mind that nothing happens until the clock makes a transition. In this case, we have a clocked flip-flop that's triggered by the positive going edge of a clock pulse, the positive edge. So that means that the flip-flop will not react to anything until our positive edges occur, which would be here, and here, 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 and here. So in between these points, it doesn't matter, for example, that set goes from low to high right here, and reset goes from high to low. It doesn't do anything. It doesn't change anything. The only time the output changes is at the points in time that I've highlighted. So here's what the waveform for the SR flip-flop would look like. If we start from the beginning, we're going to assume the output was initially 0. The first time the clock makes a positive transition, it's going to transition based off of what S and R are, what levels they're at this particular moment in time. At this moment in time, they're both 0, so this would be no change. The next point in time that matters is the next time the clock makes a positive transition. So we don't really care about what happens in between. It doesn't affect the output. At point C, that's the next time the clock makes a positive transition. That's the next time the output might change, depending on what S and R are. Here we can see that S is high while R is low. Go to your truth table and you can see that when S is high while R is low, the output should be 1. That's the set state. And that's why we see the set state happen right here in the waveform. Again, we don't really care about what's happening at point D because that's not a positive transition. So go to the next positive transition, look at S and R, and then identify what should happen next. Based off of the inputs at this point, S is low while R is high. That would be the reset state. So we can see right here the output goes back low at this point in time. And then it stays low until the next point in time that we're going to investigate, which would be the next positive transition right here. With the next positive transition, we can see that S is high while R is low. Again, that's the set state. So at this point, the flip-flop becomes set. And then we can see that it continues to stay in the same state, the set state, so it'll be set again. This is how we do the waveform for a flip-flop that has a clock signal. You can only change the output when the clock makes the right type of transition for that flip-flop. Anything in between those transitions has no effect on the output. If you had an SR flip-flop that was triggered by a negative edge of the clock, here's what it would look like. And you know that you would only change the output whenever the clock goes from high to low. Same truth table as before, except now the clock inputs are pointing down. This tells me that it responds to a negative edge of the clock. This is what the internal circuitry of an SR flip-flop looks like. You have an edge detector, some NAND gates. You have your feedback loops here. This is a NAND latch. So this is actually what's going on inside of the flip-flop. This is where your clock signal goes in. The edge detector determines when there's a rising edge or a falling edge of the clock. The next type of flip-flop we're going to discuss is the JK flip-flop. It operates just like the SR flip-flop, except that J is considered to be set, K is considered to be clear. Instead of using S and R, it uses J and K for set and clear. The major difference between this flip-flop and the SR flip-flop is that when J and K are both 1, the result is not ambiguous. Instead, when J and K are both 1, the output will toggle from its previous state. Toggle just means it'll be inverted, it'll flip. If the output was previously 0, a toggle means the output is now 1, and vice versa. This flip-flop is much more versatile than the SR flip-flop because it has no ambiguous states, and we can use the idea of a toggle to do a lot of different applications. Here's what the JK flip-flop looks like. Notice in the diagram, S and R have been replaced with J and K. That's how you know it's a different kind of flip-flop. The clock signal is right here. There's no bubble, which tells me that it responds to a positive transition. And here's my truth table. When J and K are both low, the output will not change. When J is high while K is low, the output will be set. When J is low while K is high, the output will be cleared or reset. When they're both high, this is when the output will toggle. That just means whatever Q was before, it has now been flipped or inverted. So now we're going to do a waveform for the JK flip-flop. Notice that this flip-flop responds to a positive edge of the clock, so that is the only transition we're going to be looking at as we determine what the flip-flop does. So that means I'm going to be looking at point A, point C, point E, point G, point I, and point K. If these aren't labeled on your problems, like if you're doing a practice problem and that's not labeled, you'll want to label on your paper. I typically use dotted lines or something like this, but you're always going to want to label where are the transitions that I care about so that you don't mistakenly look at the wrong transitions. So these are the transitions we're going to look at, and we're going to determine the output for each one of these points. We're going to assume that the initial condition for the flip-flop is that Q is 1. That's our initial condition. Q is 1. So at point A, we can see that J is 0 and K is 1. Go to your truth table and that'll tell you that the output has to go low. That's the reset state. And that's what we see happening right here. The next point that we are concerned about is the next positive transition on the clock, which is right here. At that point in time, you'll go up and you'll look and see that J and K are both 1. That's a toggle. So since the output was low just before this point, it'll now go high at this point. The next positive transition is at point E. We can see that J and K are both 0. According to the truth table, that means no change. So it's going to stay high. The transition that's important is right here. We can see that J is high while K is low. That would be the set state, where the output is 1. It's already 1, so it's just going to stay 1. At point I, that's the next clock transition that's important. We can see that J and K are both 1. At that point, we can see that the output will toggle, because according to the truth table, if J and K are both 1, there will be a toggle. At point K, we can see that J and K are still 1. That's another toggle. So we have a toggle here from 1 to 0. Another toggle would be from 0 to 1. And that's how we do the waveform for the JK flip-flop. If you had a JK flip-flop that responded to the negative edge of the clock, you'd have to look at the symbol here and see the bubble. If you saw a bubble, you'd do the same example we just did, except now you'd only be looking at points B, D, F, H, and J, and doing the output based on those points instead of the ones we used. This is the internal circuit for a JK flip-flop, very, very similar to the SR flip-flop. The third flip-flop we're going to discuss today is the D flip-flop. The D flip-flop has one data input. The D flip-flop's output will match the input whenever a clock transition occurs. And so what's going to happen basically is it will store the value of the input at the instant a clock transition occurs. Here's the symbol for a D flip-flop. Here's our one input. The D flip-flop is the simplest. There's really not much to remember. All you have to know is that when the clock makes a transition, Q is whatever D is at that point. That's it. So if D is a 0, when the clock makes a transition, Q is 0. If D is a 1, when the clock makes a transition, Q is a 1. That's all there is to a D flip-flop. So now we're going to do a waveform for a D flip-flop. At the top, here's my data input. Here's my clock signal. I can see from the image that it responds to a positive transition. And whatever D is for each positive transition, whatever D is what Q will become at that point in time. So if Q is initially 1, at the first clock transition, D is a 0, so Q becomes a 0. At the next positive transition, D is a 1, so Q becomes a 1. At the next transition, D is a 0, so Q becomes a 0. At the next transition, D is a 1, so Q becomes a 1. At the next transition, D is a 0, so Q becomes a 0. That's how a D flip-flop works. Again, we don't care what's happening in between positive transitions. This transition right here doesn't do anything. Only thing that matters is what is D at the point that the clock makes a transition. That's the only thing that matters. You also going to have a D latch, where the clock is replaced with an enable. The data won't be present at the output unless enable is asserted. So if you want to have a little bit more control over when the data is present at the output, you replace the clock with just an enable. So if this enable isn't 1, then the data does not go to the output. Lastly, we have flip-flops with asynchronous inputs. So there may be times when you want to override the state of a flip-flop regardless of the clock. What if I want to force the flip-flop to be high or to be low before the next transition occurs? So far, we've only discussed synchronous control inputs like set and reset, J and K, D. Those are all control inputs that are synchronous. They are used in conjunction with the clock to trigger the flip-flop. But there are also inputs called asynchronous override inputs that can be implemented into a flip-flop. Here's what that would look like. This is a JK flip-flop. It responds to the negative edge of the clock. Here's J, here's K, and then these at the top and bottom are your asynchronous override inputs. Notice that they are active low. You see the bubble, you see the bar. Active low. So the preset input is an input that will override the flip-flop. You can force the flip-flop to be high using this input. You can force the flip-flop to be low using the clear input. And this will happen immediately, not when the next clock cycle occurs. It will happen instantly. In order to use these inputs, they're active low. That means you have to send a low signal if you want to use that input. So if you want to force the output of the flip-flop to be high, you have to send a low to the preset input. If you want to force the output of the flip-flop to be cleared, you have to send a low to the clear input. These inputs are active low, so they don't do anything unless you send a low signal, meaning you would connect these to ground if you wanted to use them. And that's what the truth table shows you right here. So you have an asynchronous clear if you send a low signal to the clear input. You have an asynchronous preset if you send a low signal to the preset input. And you wouldn't try to clear and preset at the same time. That's why that's labeled as invalid. If these inputs are high, the flip-flop will work as normal, like a normal JK flip-flop. But it's when either one of these goes low that you will then see the flip-flop will be forced to be high or be low, and it'll stay that way as long as either one of these is low. So let's see an example. Here's our JK flip-flop. It responds to the negative edge of the clock. So now we're looking at negative edges instead of positive ones. J and K are both tied to 5 volts. That means J and K are both 1. That means every time the clock makes a negative transition, the flip-flop is always going to toggle. If J and K are both 1, that's the toggle state. So J and K are always going to toggle unless a low is being sent here or a low is being sent right there. So let's take a look at the waveform for this flip-flop. So initially the output of the flip-flop is 1. That's our initial condition right here. When we have our first negative transition, we're going to get a toggle. But before the next negative transition happens, preset goes low. That input has been activated. And that means it's going to go high immediately, not when the next clock cycle occurs, immediately. And that's what we see at point B, an asynchronous set, because preset has gone low. It's an active low input. You have to supply a low to use that input. If I want to preset the flip-flop, I'm going to have to send a low, and that forces the output to be high. At point C, a negative transition on the clock occurs, and we'll have another toggle. Remember, J and K are always 1, so it's always going to toggle when the clock signal occurs. So at point C, we can see that toggle happening. At point D, we have another toggle. Here's our negative transition. We have another toggle. So we have another toggle. Take a look at point E. Before the next negative transition occurs, we have a clear input that has been activated. Active low. That signal has gone low. That means we're going to force the output of the flip-flop to go low. Keep in mind that when the next negative transition occurs, it occurs while clear is still low. These inputs, the pre and the clear, they take precedence. If either one of these is low, the clock signal does not matter. So the clear will override the clock signal at point F. And nothing is going to happen because this is overriding everything. This signal being low forces the output of the flip-flop to be low and stay low. And it won't change until clear goes back high, and then we have another negative transition. So that's why you see this staying low all the way till this point. The next toggle won't happen until the next negative clock transition occurs after clear goes back high. As long as this is low, it's in control, and nothing else can change the output aside from this input. As long as preset is low, nothing else can change the output. These inputs here have to be high before the clock can do its job. That's how asynchronous override inputs work. Just remember that if clear or pre go low, the output is forced to be high or low, and it will stay that way until these inputs go back high.